Welcome everybody to our first video for the course. In this video, we'll talk about how the course is set up, the different parts, and then we'll also start talking about the first part of the first part. So let's go ahead and get started. The course is broken up into the 6 parts you see here. Part 1, we'll talk about what I call physics preliminaries. Now we're studying light, which formally is called optics. Optics is the study of light and how it interacts with matter. Optics is a branch of physics. Physics is the science really of everything. It's the science of, or the study of, the physical universe. So when I say physics preliminaries, I'm really saying basic science preliminaries. But because we do have to know something about some physics terms, physics concepts to see how we model light, how we do optics, I've entitled it Physics Preliminaries. Then what we'll do in the next part of the course is we'll get our first model of light, which is the electromagnetic wave. So we'll have to talk about some wave preliminaries, what we mean by a wave, and exactly what does a wave look like, how do we picture it looks like, what do we mean by an electromagnetic wave. In part 3, what we'll do is we'll use what's called the geometric optics model. So we're going to say that light is a wave in part 2. However, there are many optical phenomena, many interactions involving light, where you can use what I call a stripped down version of this wave model, the geometric optics model, where you're still concerned about some of the wave-like nature of the light, wavelength, frequency. But what's really important in modeling what we're observing is the direction that the light travels. So we call that geometric optics, when we can get away with just worrying about what direction does the light travel. We don't have to worry about what I call the full-blown wave picture. However, there are many phenomena where you do have to consider the full-blown electromagnetic wave model in order to model what you're seeing, to understand what you're seeing. So we call that physical optics. So we'll look at physical optics in part 4, which really is a generalization of the geometric optics model. And in part 4, we'll encounter things like interference, diffraction, polarization. Then in part 5, what we introduce is a different model of light called the quantum optics model. There we'll introduce the concept of the photon, a bundle of light energy. We'll see that some phenomena, optical phenomena, can't really be explained with the wave model, either geometric or physical optics model, and this new model has to be used to understand or describe what's going on. So that's called the quantum optics model. And then in part 6, what we'll do is we'll talk a little bit about relativity theory. We'll see how light is involved in that theory. And it's a very, very interesting theory. You may have heard of Albert Einstein. He developed this theory of special relativity, which is what we'll look at first. But he also developed an extension of that called general relativity, which really is a model of gravity. And we'll also talk about a little bit about general relativity, and again, see how light is involved in those theories. Okay, so let's go ahead and start with part 1. And I'm going to break part 1 into a few videos because I want to try to keep the videos not too long. Okay, so what I'm going to call part 1.1, what is physics? How do you do it? And why? We could also substitute science for physics. What is science? Again, physics is the study of pretty much everything in the physical universe. So sometimes I use those terms interchangeably. This video will just concentrate on those first questions. What is physics? How do you do it? And why? And then in subsequent videos, we'll talk about scientific notation and units and conversions. Okay? All right, so what is physics? Right? I've said it a couple times now. What it is the study of what we call the physical or natural universe. And I know that sounds a little circular because I'm using physical in the definition of what is physics. But when we say the physical universe, what we mean is what is the simplest the simplest composition of the universe around us in terms of what we observe to occur naturally. So it turns out, and we'll mention this again in another video, if we think about it, there are just two things in the physical universe, and that's matter, stuff that has mass and occupies volume, and the sort of nebulous concept of energy. And so we say there's matter and there's energy. And again, we'll talk about this in much more detail in a subsequent video. But what we'll say is that matter needs energy to make other collections of matter speed up or slow down. That's the basic gist of it. But the study of the physical universe then, I mean, that is a lot to study. And that's why there's so many branches of physics. But even chemistry, right? If you think about it, chemistry really is physics. It's the study usually of atoms and molecules, although you can do nuclear chemistry, which is nuclear physics. So it's what I would claim it's the one true science, but I say that with a smile. Okay, so what is in the physical universe? I already mentioned that. There are two things, matter and energy. Again, we'll see this question and these answers in another video. But matter, again, is just stuff, atoms, molecules. But we now know that there are even smaller particles that make up atoms. And there are even particles flying around that aren't part of atoms. Fundamental particles that are flying around, as well as composite particles, things like pi muons and other things. I'm sorry, pi mesons or mu mesons. So there's matter. Matter, again, it's stuff that occupies a volume and has a mass. And then there's energy. Again, hard to define energy with a straight definition. It's easier when you describe what energy is required to do. And again, energy is required if one collection of matter wants to speed up or slow down another collection of matter. Okay? All right, and again, we'll look at that in more detail in another video. I think I've said that 5 times now. Okay, so we know what physics is. It's the study of the physical universe. Optics is a part of that, looking at how light behaves. How do you do physics? Or I could ask, how do you do science in general? Good science, good physics. Well, this is the scientific method. So I'm sure you've heard versions of the scientific method. I'm going to define the scientific method in 4 steps. Again, depending on who you ask, you might get 3 steps, 5 steps, but the core of all these different descriptions is the same. And the scientific method is really what distinguishes good science. Okay, so if the scientific method is not being followed, then the results or predictions of whatever model the people have made up is questionable. Okay, so what are the 4 main parts of the scientific method? First is what I would say define the question. What is it you want to study in the physical universe? Now, if you think about it though, really a pre-step to that would be you have to make an observation, right? So you have to notice some physical processes. You have to have your senses open to nature and observe some physical phenomena. It could be a rock falling off a cliff. I always use that as a basic example. Or water running down a hill in a stream, or lightning flash. Okay, so yeah, there has to be a preliminary observation, but then when you start to do science, you're doing more than just saying, oh, look, there's a rock falling, right? You start to wonder, why is that rock falling? Or what affects how fast that rock falls? Does the rock fall the same way every time it's pushed off this cliff? Okay, so you define a question after you've made some preliminary observations. But I'm going to say number 1 is define a question. We're assuming we've already observed some physical phenomena or phenomenon. Okay, then what you do after you've defined the question is you go back to observing. But you're going to do observing in a very special way. We'll look at that on the next slide. Once you've made your detailed observations, then you are going to build a model. We're going to try to relate those observations in some meaningful way. Hopefully you can build a model, some people might call this a theory, that makes predictions, that not only helps you understand what you observed, but it also can tell you what should happen if you change one of the parameters in the process that you observed. And that's the real benefit of building these models. But then here's probably the most important step. You must test the model. So once you have this model built or this theory stated, you have to test it. If you can't test it, it's nothing more than an untested theory. And it doesn't really carry nearly as much impact or weight, no pun intended, than if it has been tested. So how do you test it? Well, let's look on the next slide. Okay, so define the question. Let's flesh this out a little bit. Why does this physical phenomenon occur, you might ask? Why does the rock fall down to the ground if I push it off of a cliff, right? What physical factors may be involved in this phenomenon? So getting back to the rock, if I go to a higher cliff and push off the same rock, does it take the same time to hit the ground? Is it traveling faster when it hits the ground? What if I try the same cliff but a different size rock, right? So what physical factors might be involved in this phenomenon? That might be a question that you ask, or a couple different questions that you ask. Now, when we do the observations, what we're going to do it in a meaningful way is we're going to define what we call physical quantities. And we want to measure these quantities using different measuring instruments, and we want to make sure that we have standardized units. Okay, so for instance, if we're looking at the rock falling, right, what physical quantities might be involved in determining, let's say, how fast the rock hits the ground, right before it hits the ground? How fast is it traveling? Well, you might need a physical quantity of distance, height, time, speed. How do you even define speed, right? Maybe acceleration is important. Maybe temperature, air pressure, mass of the rock, right? So you think about all these different physical quantities that you might have to measure. And who defines these physical quantities is us, right? So throughout history, different physical quantities have been defined because it turns out that they are useful in understanding or at least modeling the physical behavior. Now, measure is very important because if we just say, oh, I'm going to define this quantity called height, but you have no way of measuring height other than saying, oh, that looks higher than that, you're not going to get very far. So measuring is important, and that's where standardized units come in, right? So if we're going to have a unit of length, for instance, the meter, we better have a way to define or standardize a meter. And there are ways to do that. Ways have been established to define what we mean by 1 meter, or 1 inch, or 1 second, if we're talking about time, or 1 kilogram. There's a way to define that. Okay, so those well-defined or standardized units are important, not only for your own experiment, but so you can compare notes or your results with other people's results. So somebody halfway around the world can do the same experiment, and you know that their meter is the same as your meter. That's very important. Okay, so that's the best way to observe, is to measure these physical quantities that you've defined with standardized units. Then what you do when you build the model is you're simply trying to relate the physical quantities. How do they depend on each other? Now, this is usually where math comes in, where we have formulas, equations, laws. So for instance, maybe I can get a relationship between the impact speed of that rock and the height of the cliff. Maybe there's a formula where that speed depends on that height, or the time of flight, how long it takes for the rock to hit the ground once it's pushed off the cliff. I might be able to relate that with a formula to height, right? Maybe there's a dependency on air pressure, because maybe the air pressure affects, or the humidity affects how the rock goes through the air. So you're relating the physical quantities, and again, usually with math. Math really is the language of physics, because it's a very succinct way to relate quantities through formulas, equations, and laws. Then what you want to do again is test the model. So once you have this formulation, this relationship, you want to be able to test it. And the best way to test is to do experiments. So you do more experiments, controlled experiments, where you see, is the model predicting what I'm seeing in the experiment? So if I have a relationship built, let's say I have some formula built now for how long it takes that rock to hit the ground if it's pushed off of a certain height. If I change the height, my relationship, my formula can now predict how long it should take. You see? So how do I test it? Well, I just try different heights and see if that prediction is true for all of those different heights. So experimentation is key to testing the model. Now, what happens once you do the experiments and you get your results? Well, if your results don't agree with your model, you may have to adjust your model. And that's happened throughout history. Or it could be that the model is okay, it's just that your experiment isn't refined enough. Your results have too much uncertainty. So you may have to refine the experiment a little bit, or it could be a combination of both of those. And this is really an endless cycle. The models that we have now, like for gravity, some of these models have been around now for hundreds of years, but we're still doing experimentation and fine-tuning them and adjusting them. Okay, so this is a continuous process. So once you do step 4, you may be back to step 2. You're doing more observing. You might be going to step 3 and adjusting the model. So you're tweaking this, tweaking this. Now, how do you know when you're done? Well, you really never will be done. But a key of a good model, what you try to do is you try to get a simple model. That's what good science really wants, right? Who wants a complicated model? So you're trying to get the simplest model that you can, but you want it to be general. You don't want to have 1,000 different models for 1,000 different physical phenomena, right? You might want just a few models that can explain 1,000 different things, okay? So it turns out, for instance, for the rock falling, the theory of gravity and how things move through air, that will get you a really good prediction of how long it takes the rock to hit the ground. But it turns out that model of gravity, right, is not just great for determining how fast it takes rocks to fall. It also can tell you a whole bunch of other stuff, from how the planets move around the sun, how the Earth moves around the sun, how the moon moves around the Earth. So that theory of gravity turns out to be a really general model that can be used. Okay, so that's the scientific method. You guys should be familiar with these 4 steps and also be able to describe them in a bit more detail like you see on this slide, okay? I guarantee you, you will be quizzed or tested on the scientific method because it is at the heart of all good science, all good physics. Okay, so things to consider about good science, good physics, and the scientific method. And we can discuss some of these in class when I see you too, but just what I call things to consider. Models should definitely be tested with experimentation for validation. Okay, if somebody comes up with a model and says, I have no experimental proof that what I'm saying is correct, then I'm sorry, but if there's another model that predicts what you're predicting, it's a different model, and we've done experimental proof, we have experimental proof that this second model works, I think we're going to take that model, okay? Because your model hasn't been tested, okay? All right, so model should be tested with experimentation. Experiments that you do should be repeatable with same or similar results, okay? So just because a group, let's say over in Europe, has done one experiment for a new model, that's great, and they get results that the model predicts, that's great, but we better have some other groups do the same experiment, and we better get the same or similar results within experimental uncertainty, right? Our equipment might be a little bit different. So experiments should be repeatable. One experiment is not enough to say, yes, this model is 100% successful. It works all the time. Okay, models may not be able to predict a physical outcome with 100% certainty. That's true. Okay, so that's okay. That's the way science works. Now, some models can give you much better probabilities of a certain occurrence than other models, but a model may not be able to tell you with 100% certainty this is going to happen. Okay, there might be too many parameters involved, or it could be something fundamental about nature. For instance, I'm thinking of something called quantum mechanics. Quantum mechanics is the physics of the very small subatomic particles, and atoms actually too. But a tenet of quantum mechanics is that you can't actually determine something with 100% probability. It seems like nature just isn't built like that, at least the observations that we see. Okay, so a model may not be able to predict a physical outcome with 100% certainty, but that's okay. All models have limitations. They do, right? Sometimes what I say when I talk about physics is, look, all we have when we do physics are models. And what I mean by that is yes, the models might be great. These theories might predict all sorts of things. We can engineer with these models, right? We can make stuff based on the model's predictions, but all models have limitations. Getting back to gravity, right? If you ask me, why does the rock fall off the cliff? I can say, well, the model of gravity, the theory of gravity says the earth is pulling down on the rock. But you might ask, well, why is that? And I'll say, well, one of the things I'm going to state in my model is that all objects made out of matter attract each other. But you might say, why? And I might say, well, because they have gravitational mass, and two objects with gravitational mass attract each other. If you keep pushing why, at some point I just have to say, I don't know. This is what we observe. It's consistent with the model that I've stated, and that's the best I can do, okay? Science cannot answer all questions. I think I just showed you that when I was saying why. If you ask why enough times, at some point science just has to say, it's what we observe. And that's it. So it cannot answer all questions. And that's not a bad thing. That's just the way it is. But sometimes I think people forget that. I'm not saying that science is useless. I'm just saying that, yes, it has limitations, but it can do an awful lot also. So then I'm going to ask you then, considering particularly these last three things, models may not be able to predict a physical outcome with 100% certainty. All models have limitations. Science cannot answer all questions. I ask you, well, then is there truth in science? Is there truth in science? So just think about that, and we can talk about it when I see you in class. Okay, I've got to hurry up. I don't want to make my videos this long. I promise they won't be, I hope they're not this long. Okay, but let me just do this last slide, and we'll end here. So why do we do physics? Why do we do science? Again, I sometimes use those two terms interchangeably. Well, I put down 3 answers here, and I claim 2 of them are correct. And I'm being a little funny here. Well, I guess maybe you don't think it's funny, but I say there are 2 correct answers. And the 2 correct answers are number 1 and number 3. right? Yes, look, it seems like we are curious creatures. We like to know stuff. So one of the reasons we do science, physics, is just to increase our knowledge of the physical universe. It seems like we like to know stuff. We like to learn more and more. But, or I should say, and one of the benefits of gaining that knowledge is that we can actually help society through engineering, designing things, right? Designing technology, having innovations, technological innovations with these models that we've developed, okay? And yes, you can do it for the money. So I guess number 2 is correct, but I think number 1 and 3 are maybe a little bit more important about why we do physics. Although it's nice to make a little bit of money when you do it also. Okay, I am going to stop right there. Yes, because the next slide deals with scientific notation. So I'll see you in the next slide. Okay, bye-bye.